today's class. Okay, so the second problem of PLA. First of all, you should know that PLA is both array programmable. Okay, it is both array programmable. So you have and or gates here. And array is also programmable and or array is also programmable. So given two functions f1 of 0, 1, 3, 5, f2 of 3, 5, 7, implement this using 3 cross 4 cross 2 PLA, programmable logic array. In this both and or array are programmable, right? So it is more flexible compared to PROM. PROM is having only, we have or array programmable in PROM and array is fixed in PROM. Okay, so here as we know that in PLA both and array and or array are programmable, we can also generate the product terms which are not canonical in nature, isn't it? So let me solve this problem now. So 0, 1, 3, 5. Okay, first list out f1, f2 and find out which terms are common here. 3 and 5 terms are common. List out the prime implicants and try to go for minimal sum. Okay, keeping into the mind that I have already given you the size 3 cross 4 cross 2. 3 is the number of inputs, 4 is the number of product terms, 2 is the function outputs. Okay, we have f1 and f2 functions. We have to realize those two functions. 4 is the number of AND gates, that is number of product terms. So there is two solutions are there in this. You can take 5 as common here. Okay, or another solution is here 3 as common. In total you should have 4 distinct product terms. So we can see here, this is the first product term. Okay, x bar, y bar. Okay, next we have here the second product term, x bar, z. Next we have a third product term here, x, y bar, z. Next, similarly we have 5, taken 5 purposely, 5 product term common, 5 min term common, because we should have only 5 different product terms, 4 distinct product terms, 4, because the number of AND gates are 4. So this one we have x, y bar, z, and for this pair we have y, z, isn't it? So how many totally? 4 different products. Here we have 3, here we have 1, YZ. Okay, you can program these connections. Okay, the AND array is programmable, so you can program these connections. So how to do that? X bar, y bar. So x bar, y bar. Okay, x bar is here, y bar is there. It is present in F1, so put a cross mark here. Next, x bar, z. This is x bar, this is z. Put a cross mark here for x bar, z product term. Second AND gate realizes product term x bar, z. Next, x, y bar, z bar. So true form of x is here. So put a cross mark here, x. Y bar is complemented, so no bubble is there, is a complemented y bar. Next, this true form z. So x, y bar, z is available in both function f1 and f2. So put a cross mark here. Okay. Next we have yz. Okay, y is here, z is here, put a cross mark. This AND gate, the last AND gate, fourth AND gate realizes yz product term which is available in, which is present in f2. So put a cross mark in the f2. Okay, so here AND array is also programmable, OR array is also programmable. So we can generate different product terms which are not canonical in nature. Okay, so this is taking 5 as common. You can also solve this problem taking 3 as common, that is x bar, yz. Here you have 3 common, x bar, yz, isn't it? So take 3 common here. First product term x bar, y bar. Second product term y bar, z. Third product term x bar, y, z. And the fourth product term here is x, z. Okay. So totally you should make the possible combinations
Excuse me, ma'am.
in such a way that, yeah. Yes.
And some of them are
So for this particular problem, for this problem, specific problem, we have two type of solution. 5 midterm common. This solution is implemented here, and you can also implement the same solution using 3 as a common midterm. Other product terms remain as it is shown in the K map as it is depicted. So specifically I have written here 5 midterm common for these two K map, and next specifically I have written here 3 common. So I have also written here 2 possible combination solutions are there for this particular problem. Okay. So next we have, so here we have additional features in the PLA. What are those additional features? For greater flexibility, I told you earlier only, PLA is more flexible because you can see here, okay, because here we have programmable, here also it is programmable, and array or array both are programmable. We can generate the minterms whichever we require, isn't it? So for greater flexibility, PLAs make provision for either a true output or a complemented output. So true output and complemented output means what? Let me tell you here. True output means, for example, if the output is true output F1, okay, so in these all classes what we do, we realized F1 F2 functions and so on, but because of the flexibility nature of the PLA, we can also implement or generate F1 bar, F2 bar, F3 bar, like this. What does this slide says that we can generate the true output also as well as complemented output also. So this is general structure of a PLA having true and complemented output capability. Okay. So here we have Fi feeds into one input of an XOR gate. Students, this is very important. This one is very important. You should see here. Okay. So you can see here Fi feeds into one input of an XOR gate. The other input is connected to a pull-up resistor. When the fuse is left intact, the input is 0. When the fuse is blown, the input is 1. So what you have to understand here is this is important. I am underlining this. When the fuse is left intact, the input is 0. When the fuse is blown, the input is 1. Okay, this one you have to remember. This is useful for solving the next problem of related to PLA. When the fuse is left intact, the input is 0. I repeat once again. When the fuse is left, the input is 0. When the fuse is blown, the input is 1. Okay, remember this. Remember this statement. When the fuse is left, the input is 0. When the fuse is blown, the input is 1. Okay, so using this, we can also generate the true output as well as the complemented output also. So here, example of using the use of complemented functions. Example, so here I will write the functions. F1 is given summation m. F1 is given summation m 1, 2, 3, 7. F2 is given, F2 is equal to summation m 0, 1, 2, 6. What you do, students, this one, how to use the complemented functions? I will tell you here. 1, 2, 3, 7. First write it in the K map as it is. 1 is there, so put a 1. 2 is there. 3 is there. 7 is there. Group it and write the product term F1. Okay. So next 0, 1, 2, 6. So 0, 1, okay, 0, 1, 2 and 6. Group it and write as it is. Okay, so for this we will get x bar. y bar. For this we will get y z bar. Okay, so next complement. Okay, you have to group zeros. You have to group zeros here. For the zeros, what you will get here? Always remember that we always realize for SOP in PLDs, not POS. So here for this you will get y bar z bar. For this you will get x y bar. For this you will get, okay, x z bar. So write as it is, F1 bar, grouping zeros, and write SOP for this. Okay, because PLA can realize only SOPs. Okay, so next F2 bar, how do we group zeros? Write SOP for this. Okay, group zeros, write SOP for this. So here we have one pair and here we have one pair. So for that I have written here the product terms. So these are the K-map for the functions given 1, 2, 3, 7 and 0, 1, 2, 6. Okay. So here for this particular problem we have put a F1, we have found out F1, we have found out F2, we have found out F1 bar, we have found out F2 bar. Group zeros, write SOP, because PLDs can only realize SOPs, not POS. So here for the earlier one, whatever we got the product terms, the product term was like this. X bar z we got, x bar y we got, yz we got, x y bar we got. Okay. Similarly here. Okay. So what we are realizing here is F1, F2 bar. Let me tell you why. F1 and F2 bar we can realize. Why? Tell me. Can anybody tell me why? Because if I combine these F1 and F2, I get only 4 product terms, and by using F2 bar, I can generate F2. Isn't it? If I take a complement of F2 bar, I will get F2. Okay. So here, students, if you have any doubts, you can. Can I realize F1, F2? No, I cannot realize because 1 product, 2 product term, 3 product term, 4 different, 5 different. The size given is 3 cross 4 cross 2. But we are getting here 3. This is 3 product term, this is 2 product term. Totally we get 3 plus 2, 5 product terms. So we cannot realize using this size 3 cross 4 cross 2. So what we do is we cross verify whether I can do with F2. Okay, F2 bar. Can I do it? Yes, because YZ is there here and YZ is there here. So totally I will get 4 product terms, isn't it? So 3 product terms, F1 I will realize as it is with 3 product terms. Okay, so this here it is YZ, here also it is YZ. YZ is can be taken common. Okay, that will be the 3rd product term. 4th product term will be X Y bar. Using F2 bar function, implementing this F2 bar function, if I put a XOR gate, okay, with some programming, I will get F2 function at the output. I will get F2 function at the output. So what I will take is, I will take F1 and F2 bar to implement, and then I will take a XOR gate for F2 and then implement F2. Okay, right? From F2 bar we can implement F2. Okay, so that one only I will do it. So we can see here F1 product terms we have seen, we have got X bar Z, X bar Y, Y Z, and next we have X Y bar. Okay, so YZ term is product in both F1 and F2 bar. Okay, so here what happens, X bar Z is present in F1, put a cross mark, X bar Y is present in F1, put a cross mark, YZ is available, so put a cross mark, X Y bar it is available in F2, so put a cross mark, YZ is available in both. So put a cross marker F1 and F2 bar. Okay. Now it is blown means a constant 1 is present here. F1 XOR 1, I will get the output same as F1. So I have implemented F1 here. Next, when I left intact as it is, a constant input 0 is provided at the lower input of the XOR gate. So F2 XOR 0, I will get F2 at the output. So this is how we can generate the true and complemented output of the Boolean expressions. Okay, with the help of the XOR gate, if I have F1 XOR 1, if I do F1 XOR 1, I will get F1 only at the output, whereas you can see it F2 XOR 0, I will get F2 only. 0. If suppose here 0 XOR 1, okay, so 1 means here I'll get the complement of it. So we can use Fy XOR 0, Fy bar. This principle is used here. When I XOR with 0, I'll be getting the complement. So F2 will be implemented here. Okay, so in the next one, what the author has tried to do is realization of F1 and F2 bar, because we get a 4 distinct product terms here: XY bar, XZ bar, Y bar, Z bar and YZ. You can see it in the previous slide, F1 bar, F2 bar. You can see here F1 bar and F2 bar product terms. You can see XY bar is common in both, in F1 bar also, in F2 bar also. Ultimately what we have to think is we have to have 4 different product terms. Okay, so in F1 we have XY bar, F2 also we have XY bar plus XZ bar plus Y bar Z bar. Okay, 3 product terms. Here YZ, 4th product term. So what we will do is we will implement first F1 bar and F2 bar, and next use a XOR gate and blow it, and then get a F1 function implemented and F2 function implemented. Students, here by implementing F1 bar and F2 bar functions, we can get F1 and F2 also. Sometimes it is not possible to implement this F1 F2 unknown. How can I implement when there is size is given 4? Okay, but the different product terms are 5. Somehow I have to make it 4. Okay, directly F1 F2 I cannot implement it. How to do it? By using F1 F2. F1 F2 bar I used. Here YZ was common. Okay, so F1 I took as it is. By XORing with 1, I get F1 as it is. Next F2 bar XORing with 0, I will get F2. Okay, so next here I can also implement F1 bar F2 bar. This is another method to implement F1 F2. Okay, so sometimes it is not possible directly F1 and F2 implement. So what we do, we go for complemented functions. We generate first, or we implement first the complemented functions and then start implementing the true functions. Okay, by using a XOR gate. So F1 bar is there, F2 bar is there, XY bar is common. So from F1 bar function, F2 bar function, we get 4 product terms: XY bar plus XZ bar plus Y bar Z bar plus YZ. These 4 product terms, I will implement it in the second one here: XY bar, XZ bar, Y bar Z bar, YZ. Okay, so put a cross mark here: XY bar, X, Y bar. This AND gate will generate a product term XY bar. Next, X, Z bar. This will generate X, Z bar. This Y bar, Z bar. So this AND gate will generate Y bar, Z bar. Next, this one, it will generate YZ. Okay, so when it is left intact, the constant input 0 is fed in the second input of the XOR gate. So F1 XOR 0, Fi bar XOR 0, I will get the F1. F2 bar XOR 0, I will get F2. Okay, it is not connected. See here, there is a cross mark here, it is connected. If there is no cross mark, then it is not connected. So here also both are not connected. So if it is not connected, it is left intact. The constant input 0 is applied to the lower input of the XOR gates. Then we will get the complement of it. So you know the XOR operation, isn't it? When I XOR with 0, I'll get a complement of it. So Fi bar is there. So I'll get a complement means F1 I will get. F2 bar is there. F2 XOR 0, I'll get F2. Simple principle Okay, so simple principle is used of the XOR, and true and complemented functions both are implemented. So this is an example using complemented functions. Okay. Okay. So PLA table, a common way of specifying the connections in the PLA. Three inputs are there: input section, output section, T and C. T stands for true, C stands for complement section. Okay, complementary output. Each product term is assigned a row in the table. Okay, you can see three sections. See here, this is input section, this is the output section, and the third section is TC, true output, complementing output. Okay, so here input section indicates connection between to the AND array. Output section indicates connection between output of the AND array to the input of the OR array. Okay, output section is the output of the AND array which is connected as an input to the OR array. TC section indicates how the exclusive OR gates are programmed. T means true output is used. C means output should be complemented. Okay. So here I will show you how to write the table. How to write the PLA table. One table I will show. Okay. See here. For first we did know, first one means this one. I'll show you this one. This one is first, this is second. For this I am going to write a PLA table. Okay, so what is the table, PLA table? First I list all the product terms: x bar z, x bar y, y z, x y bar. All the product terms I will list first. Okay, and see here student, first you to remember this. F1 is taken as it is true output. F2 is taken complemented output. So for first I will write T. For second I will write C. Okay, is it clear? The first one I will write T, second one I will write C, because I have taken here complemented one, F2 bar. So here x bar z, x is present, x bar is present, so it is 0. Y is present? No. Z is present? Z is present? Yes, Z, so 1. Next, x bar y, 0, x bar, so 0. Y is present, 1. Z is present? No, put a dash. Y, Z, x is not present, y is present as y only, z is present as z only, 1, 1. Next, x is present as 1, y bar, so 0. Next, y bar. Okay, so you understood? If z is not there, put a dash in that. Okay, so is x bar z present in F1? Yes. Is x bar y present in F1? Yes, put a 1. Is yz present in F1? Yes, put a 1. Next, x y bar is not present in F1, so put a dash. Next, x bar z is not present in F2, put a dash. X bar y is not present in F2, put a dash. Yz is present in F2, put a 1. Xy bar is present in F2, put a 1. F1 has taken as it is, no? So I will write T. F2 was taken as complementary. F2 bar was taken, then I had applied to a XOR gate, then complemented it, then we have taken F2, isn't it? So it is C. It is C. F1 is taken as it is true. F2 is taken complemented one. We have taken implemented F2 bar first and then taken F2 next. Okay, so we have written C here. Similarly, for the second product term, second one, F2, F1 bar, F2 bar. Here we have taken F1 bar. Here we have taken F2 bar. So both are complementary here. Okay. So x y bar 1 0 z is not present, put as dash. Next x z bar 1 dash 0 y bar z bar. Okay, x is not present, put a dash 0 0 y z dash 1 1. Okay, so whichever the product terms are present in F1, put 1. Which are not present, put dash. Next, in F2, whichever product terms are present, put 1. Which are not present, put a dash. Okay, so here You can see here, okay, this one. F1 bar is implemented, then we have put a XOR gate and then taken F1 here. F2 bar is implemented first, then we have connected the output F2 bar as an input to this XOR gate and then we have taken F2. So this is also complementary, this is also complementary. So both are C. Both are C. Okay. Here you can see F1 is taken as it is. So it is T. Here F2 bar is implemented. So it is C. So here we have TC. In the first above one we have T because F1 is implemented. Here we have implemented F2 bar. So it is C. Here we have implemented F1 bar. So it is C. Here we have implemented F2 bar. So it is C. Okay. You can see here it is C. This is C and this is also C in the second one. In the first one it is T and C. Okay. So the PLA table is important. It contains input section, output section and TC section. Input section XYZ, output section F1, F2. Okay. Write the product terms, all list out all the product terms and then write it. If it is present 1, if it is present in uncomplemented, put 0. If it is not present, put dash. Whichever product terms are there, write 1. Which are not there, put a dash. Okay. If the true form is generated, write T. If the complement F2 bar or F1 bar is implemented, write C. Okay, as we have done. What these are called? These are PLA table. Okay, you understood how to write the PLA table. The third type, programmable array logic. So here OR array is fixed by the manufacturer of the device. PAL is easier to program and less expensive than the PLA. It is less flexible. It is less flexible because you can see here OR array is fixed here and AND array is programmable. Okay, it is less flexible. Okay, so it can implement 3 expressions. Okay, F1, F2, F3. It can implement 3 expressions F1, F2, F3. F1 with 3 product terms, 1 AND gate, second AND gate, third AND gate. What does this junction dot indicates? It indicates a connection to the function F1 OR gate. Next, F2 can implement second expression with 3 AND gates. F3 can implement third expression with at most 2 product terms. So F1 implement 3 product terms. Okay. So here F1 can implement F1 can implement 3 product terms. Here I will write this one, this one, this one. So 3 product terms. Okay, product terms. P means product. F2 can implement an expression with 3 product terms. F3 can implement the third Boolean expression F3, that is with 2 product terms. AND array is programmable. OR array is fixed. Fixed OR array, programmable AND array. Okay. So this understood, no? So this F1 with 3 product terms, F2 with 3 product terms, F3 with 2 product terms can be realized using this PAL device. So for our example, we have 4 input, X1, X2, X3, X4. Okay, for our example, it's a standard one. Okay, 4 input is there, 3 outputs PLAD. 3 output means F1, F2, F3, 3 output. Okay, X1, X2, X3, X4, 4 inputs, 3 output PAL device. 3 Boolean expressions can be realized in which 2 expressions can have at most 3 product term and 1 expression can have at most 2 product terms. The same thing I have told. This PAL device can implement 3 Boolean expression. Okay, 2 expression can have 3 product terms. 1 expression can have 2 product terms. So let us solve a problem in this. Take an example how to solve this PAL. F1 is given x, y, z, summation m of 1, 2, 4, 5, 7. F2 is given x, y, z, summation m of 0, 1, 3, 5, 7. Okay. So how many expressions are there, students? 2 are there, F1, F2. Okay. Group them, minimal sum, minimum grouping, group them. So 1 grouping, 2 grouping, 3 grouping, and the fourth one here. Here we have one pair and one quad. For this we have written an expression. Okay, so for the first one we have x y bar. This one is written here, x y bar. Second one, okay, here this one x z, x z. So we have written here x z. Next third one, this pair we have y z bar. Oh, sorry, y bar z. Okay, so written here y bar z. And this one a single cell. So it is x bar y z bar. So it is written here. Okay. Next expression, you have here one quad and one pair. So written here z plus x bar y bar. Okay. Students, I had told you earlier only, the standard device is having PAL is having, it can implement three expressions, two expression having three product terms, one expression having two product terms, isn't it? See how many are there here? 1, 2, 3, 4. Can I implement this function F1? No, I cannot implement this function F1 because it is having 4 product terms. I told you students that a PAL device, PAL, programmable array logic device, can implement two expressions of 3 product terms, one expression of 2 product terms. But it cannot implement an expression having 4 product terms, 1, 2, 3 and 4. Now what we do for that? We have a solution for that. What we have to do is, look at this students. Just for your reference, I will write the expression F1 is equal to xy bar plus xz plus y bar z plus x bar y z bar. F2 is having two product terms z plus x bar y bar. Okay. Now how to do this, students? It is having 4 inputs, isn't it? x1, x2, x3, x4 there in the problem, but for here x, y, z, 3 inputs. Now what I will do here is, I will break the function, f1 function. I will break like this, f3. f3 is equal to, I will write like this, x, y bar plus xz. So I have broken with f3. So f1 can also be written like this, no? f3 plus y bar z plus x bar y z bar. Isn't it? I can write like this. Can I write like this? I have broken it now. 4 product terms were there. No, I cannot implement it. So what I will do? I will break it. F3 is equal to xy bar plus xz. F3 is equal to xy bar plus xz. These two product terms. So this will become F3. So F1 can be rewritten as F3 plus y bar z plus x bar y z. So now what I will do here is, see here, F1. Okay. F1, what all it is having product terms? See here, this one, F3. So coming back to this F3, okay, F3 implements xy bar plus xz. Okay, these two product terms. Let me check this F3 first, because F1 is having F3 plus these two product terms, isn't it? So let me check F3 first. F3. Okay, I will go back the feedback in turn where F1 is connected. You can see here feedback of the F3 where F1 is connected here, F1 is connected here. There is a junction dot where this feedback it's connected to this F1. So this will be F3 plus. F3 is connected with the feedback line with using the fourth input of the PAL device. So here we have true form of that connected to this AND gate. So this will realize F3 and that is connected to F1. Fine, right? Isn't it? So next we have Y bar Z here, isn't it? You can see here Y bar Z. So Y bar Z that is connected to F1. Next X bar Y Z bar. X bar Y Z bar that is connected to F1. So in this way, by having a feedback connection from the F3 and then giving a connection to the F1, we can implement F1 is equal to F3 plus Y bar Z plus X bar Y Z bar. Now how F3 is implemented? Using this last F3, last two product terms. F3 is equal to what, students? X Y bar, isn't it? So here F3 is equal to X Y bar. It is implemented here, F3. X Y bar, isn't it? Next XZ. So this is X, this is Z. X Z. So this is implemented here. So these two product terms are implemented in F3. Here you can see this one. This AND gate realizes X Y bar. This AND gate realizes X Z. So these two are connected to this F3. This implements the Boolean expression F3. F3 is a part of F1. So it is an external connection giving a feedback link that is connected here cross mark through this junction dot to function F1. F1 is equal to F3 plus Y bar Z. This is implements Y bar Z. This implements X bar Y Z. So along with these two product terms and F3 will give me function F1 by having an external connection feedback through this fourth input of the PAL device. Okay. So next F2 I have to implement. F2 is having Z. So this is implements Z. Okay. And next XZ. So this is X. This is. So here we have. Okay. This implements Z, isn't it? This implements X bar and Y bar. Okay, X bar and Y bar. For F2 it is X bar and Y bar. Okay, X bar and Y bar. Z plus, this is Z connected to F2. X bar, Y bar, this is connected to F2. So this one implements the F2. This AND gate is not connected anywhere, so put a cross mark. Okay, this AND gate is connected to F2 but no product term is realized in this AND gate, so put a cross mark. In this way we realize a function using PAL. Okay, so these two product terms Z plus X bar Y bar are connected to this F2. Even this AND gate is connected to F2 but this is not used because third product term is not there, so put a cross mark indicating no third product term present in the function F2. So this is how we implement 3 cross 4 cross, okay, 3 cross 4 cross 2. So here 4 inputs are there, 4 inputs are there here. Okay, so we have 4 inputs here, but here just a minute. So how many inputs are there here? 4 inputs were there, no? 4 inputs. The fourth input is taken as a feedback to this. Feedback and then connected to F1. So these two expressions realized F2 function. The third product term of F2 is not used, put a cross mark, and these two product terms realized F3. F3 being a part of F1, so it is given as a feedback and connected to F1. So F1 is equal to F3 plus Y bar Z plus X bar Y Z bar. So in this way we have implemented F1 by making a subdivision F3, by taking a subdivision F3 and then taking it as a feedback and then again giving it to F1. So here we have implemented F1, F2, F3 by using this PAL device.